So we've done all of the tests, right? And and there are 1,000 of these online. That's where I pulled this one off of. Either that or I printed it out of, I don't know, or I copied it out of some book. Here's the thing. There are charts like this online that actually help sort of give you a distillation of everything that you've learned in terms of convergence and divergence thus far. And it gives you a nice sort of reference to put next to you while you're doing your homework from 11.7. So you have them all at your disposal. Now, obviously, the point is to be able to memorize them eventually, but there's no better way of memorizing than actually by doing, right? So if you don't have one of these, go ahead and stop the video and, Google summary for testing series or something like that, PDF, and then pull one down because it's going to be helpful to have it next to you while we're working some of these problems, okay? And it actually, and there's even ones that are like flow charts where it actually, first you ask this question, here's where you go if it's no, here's where you go if it's yes. If that jives with the way that you think, get one of those as well, and just put convergence, divergence, flow chart into Google, and you'll probably pop up with about 3 dozen of them. But let's go ahead and just start doing some problems because that's just the best way to actually start looking through all of these, okay? And after a while, after you've done a number of these, you just start to get kind of hunches as to exactly what's going on and why. Now, is that convergent or divergent? And if so, whichever one it is, how are we going to tell? Like, we need to actually have an analytic justification for exactly what's going on here. Well, I tell you what. Let's go ahead. Here, let me move this up just a little bit. And let's try the ratio test, okay? The ratio test I'm going to be using because I remember that I can simplify anytime factorials are involved in sort of in a rational structure like this. Ratio test ought to be one of the things that comes to mind because we can take n plus 1 factorial and transform it, right? We can turn it into n times n plus 1 factorial is n plus 1 times n factorial. And because you can do stuff like this, canceling within that rational structure actually becomes very, very possible, very, very easy and straightforward. And so ratio test is actually one of those go-to moves. So let's go ahead and let's actually talk about a sub n plus 1. We know that it's going to be n plus 1 factorial squared over 2n plus, well, when you plug in n plus 1 for n, you have to distribute the 2, right? And basically that is your a sub n plus 1. So we have the limit as n approaches infinity of n plus 1 factorial squared, all of that over, and I guess you don't need brackets for this, parentheses would do just fine. And I have 2n factorial over n factorial squared. And the question is, can I simplify that to such an extent that I actually begin canceling things out and actually leave myself with a somewhat straightforward and easy limit? And the answer is yes. You just have to remember how to change the form of these factorials, which are in the abstract in rather than a numerical form. Now, I happen to remember that anytime you're squaring something, you actually can n plus 1 factorial times n plus 1 factorial. That's what the squaring means, right? Well, each one of those can be dealt with thusly. Okay? And so you're going to have 2 n plus 1s, so we'll square that, and then 2 n factorials, and so we'll square that. Now down here in the denominator, we're going to do something similar to this move right here. It's 2n plus 2. So all we have to do to get back to 2n factorial is just deal with the two preceding numbers. Whatever 2n is, 2n plus 2 is 2 numbers higher, right? And so I can actually sort of make this move twice and basically simplify it like this. And now, excuse me, it is in a form where we can do a whole lot of canceling. Boom, 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 boom. Okay? Now, if you want to, you can go ahead and multiply it out in order to see it a little bit better. But you ought to know that that numerator is that when you FOIL it out. And you ought to know, and really the only thing that matters is the leading coefficient, right? But you can go ahead and multiply it out like that. That tells you that the limit is 1/4. Now, if the limit is 1/4, that makes it less than 1, and it converges by the ratio test. Okay? Okay, well that was relatively straightforward. Let's actually move on to another one. Okay? Let's do sigma n is equal to 1 to infinity of 5 to the n over 4 to the n minus n. Well, if this is a sub n, I happen to know that it's kind of related to that. And I know that this is divergent. And I know that when you subtract something from a denominator, you make the denominator smaller, which makes the ratio larger. So I think I could probably do this by direct comparison, right? Because I am, after all, plugging in positive integers. I'm plugging in positive numbers for n, and therefore I'm subtracting positive numbers from the denominator. The denominator is getting smaller, and therefore the value of the ratio is getting larger. So 5 to the n over 4 to the n minus n is indeed larger for all n than a known divergent geometric series, right? This is divergent geometric, and therefore what we have here is our original is divergent by comparison. I usually like to refer to it as direct comparison, so it's distinguished from the limit comparison, okay, by the direct comparison test. Okay, and the clue was it didn't have any factorials in it. It was still rational. You're not really, because this is a binomial in the denominator, it doesn't really make a whole lot of sense to go with since it's two terms in the denominator, it doesn't make much sense to go with the ratio test because it's going to have a harder time canceling things out. But you do know very, very quickly that sort of the related geometric is very easy to recognize as divergent. Okay? And basically adding to the numerator or subtracting from the denominator or vice versa to a known convergent or divergent series just screams direct comparison to us, or it should. Alrighty, let's go ahead and look at sigma n is equal to 0 to infinity of 2 to the n arctan n to the n, all of that over e to the n. Now, there's a whole lot of to the n power. Well, that just means that what we're doing here is probably the root test. So let's go ahead and do the limit as n approaches infinity of 2 to the n arctan n to the n over e to the n, and we're just going to raise that to the 1 over n power, which is the same thing as actually doing the root, right? Let's go ahead and actually push that fractional exponent into here and actually see what transpires. We wind up getting 2 times the nth root of arctan n to the nth, right? Because the nth power right here was not raising the function to the nth power, it was raising the ratio right here. Remember the thing what inverse trig does is it takes a ratio and turns it into an angle measurement. This is a ratio right here. It's the ratio that's being raised to the nth power and not the function. Okay, so we need to be very careful about that. But we happen to know what happens when you take any quantity, and of course arctan, as n goes to infinity, all the raising to the nth does is just speed up the rate at which arctan is going to approach the pi over 2. Okay, so this radicand right here is approaching pi over 2 as n goes to infinity. Excuse me for a second. That radicand is approaching pi over 2. So if the radicand is approaching pi over 2, but the root that it is being taken of that pi over 2 is approaching infinity, then this whole quantity is actually approaching 1. Okay? Now what that means is the fact that that should be 2 over e. Okay? And 2 over e, since e is larger, okay, winds up being a little bit less than 1, and therefore what we have here is a convergent series by root test. Okay. Now, what would happen if that to the nth power was actually not to the ratio but to the whole function? Well, let's see, okay, because in fact it makes all the difference in the world. So we have n is equal to 0 to infinity of 2 to the nth, and we'll say arctan n to the nth, okay, e to the nth. Now that is very different from the original, okay? The original was the n being raised to the nth power. This one is the whole function being raised to the nth power, and therefore when I take the limit as n approaches infinity of 2 to the n, arctan n to the n, e to the n, to the 1 over n, right, because that's the nth root right there, I wind up getting the limit as n approaches infinity of 2 times arctan n over e. Well, this winds up approaching 2 times pi over 2 over e, or pi over e, that is greater than 1, and therefore is divergent. Okay, so whether the angle measurement was raised to the n or whether the whole function was raised to the n is the determination. It makes all the difference in the world as to whether it's divergent or convergent by the root test. So be very, very careful with your notation, and if it's ever seemingly ambiguous, always ask. Right? Well, let's go ahead and move on to the next one. Let's say we have n is equal to 1 to infinity of 1 over n plus 1 root natural log n plus 1. Now, what is this? Well, it's probably not going to be ratio. It's definitely not going to be root. It doesn't look geometric. It doesn't look like a p-series. I don't really think direct comparison is going to work, but that does look a whole lot like a function that function, which tells me that if I were to actually put that into an integral like this, I have u du. So I actually can deal with this by way of integral test. And this winds up being, if that's u to the negative 1/2 du, that becomes u to the 1/2 over 1/2, or 2 u to the 1/2. Okay? And of course we have to deal with the limit as b approaches infinity of 1 to b, right? Because we're dealing with an improper integral. And so we get the limit as b goes to infinity of 2 times the square root of natural log b plus 1 minus 2 times the square root of the natural log of 2. Well, this is obviously a constant, so we're not really worried about that. But as b goes to infinity, what happens to this term right here? Well, that term goes to infinity. So this is divergent, the integral right here. And so the related series right here, this is divergent by the integral test. Okay? Now, that should be relatively straightforward. Yeah, I'm hoping. We're going to go ahead and do at least one more video, perhaps two, in order to sort of iron this out. You'll probably have a couple days worth of homework on this as well to iron it out. But as always, if there was anything in this video that was unclear, go ahead and shoot me an email, and I will look forward to that. And I will go ahead and get busy on video 2 for 11.7. Bye.